Good morning, everyone. Welcome to today's GoFly Master Lecture. We're so pleased that you could join us. I'm just gonna share my screen here. So GoFly is sponsored by Boeing and is joined by a number of partner organizations. We're so excited that the GoFly community is now nearing 2,500 in its community across 90 different countries. Today, we're happy to welcome Dr. Steve Rizzi, Dr. Doug Nark, and Dr. Nikolas Zawodny, who will be lecturing about rotary wing noise. So Dr. Steve Rizzi is a senior researcher for Aeroacoustics at NASA Langley Research Center. He leads NASA's perception influence design effort to help develop revolutionary tools and methods for low noise design of transformative vehicles. Dr. Doug Nark serves as the NASA Langley Technical Lead for Acoustics for the NASA Advanced Air Transport Technology Project of the Advanced Air Vehicles Program. And Dr. Nikolas Zawodny is a Research Aerospace Engineer of Aeroacoustics Branch at NASA Langley Research Center. And so with that, I'll go ahead and pass it over to the team to start their lecture. Really excited, guys.
Thank you for that introduction. Can you see the PowerPoint presentation okay?
Not quite yet.
Not yet. All right. And is that still the case?
Yeah, still not yet.
Okay, sorry for that. I'm hitting share screen and, oh, okay, it's asking me which screen, sorry. The show.
Great.
Okay. Still all okay, right?
Yeah, all good.
Okay, thanks. Thank you for that nice introduction. I'm Steve Rizzi here, and beside me is Doug Nark and Nick Zawodny. And today we'll be giving you a few tips, nothing too technical, but hopefully enough that you can come away with something useful for your team. And of course, these tips are related to acoustics for design of quiet, near VTOL personal flying devices, and that's what this is all about. I thought we would start off a little bit easy here and tell you a little bit about ourselves. So I'll let Nick go first, and Doug go first, since he's on the leftmost panel, and that's yep. He can tell you that's not him in his earlier days.
Yeah, that's me earlier days. No, that's Tanner. He photographs much better than I do, so I had to put that one up. Actually, with the information there, just even in terms of the introduction, as we mentioned, I'm just a senior researcher in the Structural Acoustics Branch here at NASA Langley, and have been doing work over the last 20 or so years on propeller rotor noise and the noise sources themselves, and then the subsequent scattering of it. So I have a couple of slides here at the beginning that hopefully provide some useful information.
Okay, thanks, Doug. Pictured above there is my first solo flight at age 15. I like to say that, and it's true, that I learned to fly before I could drive, and so it's stuck, and I've been in aeronautics ever since, really. So I invited Doug and Nick to join, and glad to have them accompany me on some technical expertise, offering technical expertise that I frankly don't have myself. So got some heavy hitters in here. And Nick?
Yeah, I'm Nick Zawodny, and admittedly, Tanner and at least young Steve do photograph better than I do. But so I just hit my 5-year mark here at NASA, and started off working with open rotors, basically spinning blades in various forms. Originally did landing gear research when I was back at UF, but been looking into interaction mechanisms, which I'll give you some highlights and just some observations that I've made in the past couple of years.
Okay, thanks, Nick. So the talk will go as follows, and I guess either Sky or Paul will moderate, but we've got a brief introduction, and then we're going along the lines of how we traditionally think about acoustics for vehicles. That is, looking at the source, the installation of that source, noise mitigation, because it will produce noise. And then I'll be speaking about kind of how it all, what that all means insofar as the GoFly noise goal, and offer up a couple of NASA's noise prediction tools that are at least available to some of the community. So with that introduction, I'm assuming that the community maybe knows a little bit about noise, but probably not so much. So this is perhaps a bit tutorial. But the sound pressure level is a measure of the noise. And that noise or that expression is, it's measured in a decibel form in dB, given by the expression on the upper left, where the sound pressure level is 20 times log base 10 of the root mean square pressure divided by the reference pressure. The reference pressure in air is 20 micropascals, and that is considered to be the threshold of human hearing. So 1 Pascal is equal to 94 dB, and just by kind of reference, 1 atmosphere is about 101,000 pascals. So the amount of pressure that we're talking about, acoustic pressure, is very small compared to the ambient pressure, as the atmospheric pressure. You'll hear about this a little bit more shortly, about the different types of sources of noise, but they may add up differently. It could be adding coherently. So for example, if I have 2 propellers or rotors spinning nominally the same, and they're emitting noise at then about the same level, then we would add them coherently so that there is a 6 decibel increase per doubling of the number of sources. And if you have more than that, then you can use the expression shown at the bottom of the page. Conversely, if I have a propeller and a fan that's unrelated to it, those would add incoherently, and so that's a 3 dB per doubling. Now, the way the rules are specified, the sound pressure level is going to be measured as a A-weighted sound pressure level, given by dBA or LA, as indicated on the upper right-hand side. And so what that means is that certain frequencies are weighted more or less than others. And the blue curve shows the A weighting curve, which is the inverse of the equal loudness curve for low sound pressure levels. And those levels are, or this A weighting is applicable at 40 Fon, but is actually used for pretty much all sound levels. So what this curve is saying is that in order for me to, for a human to hear the sound at, say, if I can make out the figure, 100 hertz, I need to boost the level up by about 20 dB compared to what it would be at 1000 hertz. And so this is very important to know, because this is how the sound is measured for the purposes of this competition. It's also how we interpret the sound or perceive the sound. And therefore, if you're going out and measuring the sound of your device, you should be using a sound level meter that has A weighting applied. And I'll be speaking to that more in later on in the talk. So I think with that, we'll go to Doug.
Okay. Thank you, Steve. As Steve mentioned, the way we've kind of tried to outline this is sort of begin with some of the isolated source mechanisms, tell you a little bit about that, and then Nick will come along and kind of talk about how they interact once these things are installed. And just sort of to set the stage, what we thought would be a good idea here is to give you an example of a nominal vehicle and show you what some of the possible noise sources would be as that vehicle is in a VTOL or a vertical flight state, or conversely on the right hand side there in a cruise sort of flight condition. And so to begin with, what we'll do as we go through these possible source mechanisms is talk about them in terms of two broad categories, that being the deterministic or tonal, and that would be what we'll refer to as, for example, if you have a rotating propeller, that will rotate at some particular RPM, and based on the number of blades, you will get a blade passage frequency. And so that noise source itself will look very tonal. At specific discrete frequencies, you'll have a signal. Conversely, there's also what are called broadband. There's broadband sources as well, and you can think of those as they're not deterministic. Those are going to show up over a broad frequency spectrum, so to speak. And so depending on the source mechanism, you'll see them coming out as being either tonal or broadband. And so starting out in the vertical flight envelope that we've got there on the left hand side, you can see, for example, as that vehicle is flying, what you'll end up with is some interactions. First of all, with just turbulence that's in the atmosphere itself will interact with the blades and cause some unsteady noise that we'll talk a little bit about. Then from the downwash of those rotors, what you're going to have is sometimes termed fountain flow, which is flow that actually interacts with the fuselage. And in general, those are going to turn out to be, there'll be some tonal aspects of it, but you'll also see quite a bit of broadband noise from those. You can see there's also an arrow there pointing to the actual blades themselves. And that's where we're going to start talking about the sources in terms of an isolated blade. As that blade rotates, you're going to see just noise due to the blade thickness and the actual steady loading on the blades themselves, whether that be in vertical or in horizontal flight. And then you see as the right-hand side, when it's in horizontal flight, you're also going to see further interactions. For example, if the configuration maybe has tandem rotors, you might see some blade wake interaction as the wake from an upstream or a forward propeller interacts with one that's downstream. So you'll see that not only from the wake, but also from the tip vortex. And then for an isolated propeller itself, obviously something's got to be turning it. So we're going to have some contribution due to the actual engine or motor that's actually turning it. And so I think with that, what we can do then is talk a little bit more specifically about those isolated sources. And we'll sort of begin from the fundamental level of how we go about predicting what the noise due to those sources is. And so we don't have a ton of equations on here, but this seemed like a nice way to sort of introduce you to how we think about the isolated blade source mechanism itself. And one way to kind of frame that is through the use of the Fox-Wings-Hawkins equation, which is really just a rearrangement of the full Navier-Stokes equations into an inhomogeneous wave equation. And by that, we mean what happens is essentially you've got a wave equation, and on the right-hand side, we have these source terms that essentially are going to sort of give you some indication of what these isolated blade sources are. And we've labeled them there, the first one being the thickness noise. And you can think of that as that's really just the contribution or the effect of the blade moving through the air. So, basically, as the name implies, if you have a thicker blade, that contribution to the overall noise would be greater. Thinner blades, obviously, would be less. But that thickness noise, again, is just due to the displacement of the fluid as the blade moves through the air. Then in addition to the thickness noise, you'll have loading noise, and that is due to an accelerating force distribution on the blade. So essentially, those fluctuating blade surface pressures, the pressures on the blade as that blade moves, are going to cause an additional source that we refer to as the loading. And that we'll talk a little bit more, but we have both steady and unsteady loading. So essentially, if you have a blade that as it's moving through the air, because it's accelerating, even if that distribution is steady, that will cause noise. And then the third term on the right-hand side there, we have what is called the quadrupole term. Those are generally those are volume sources, and generally there will be some there's some deterministic or tonal aspects to that, but for the most part, the majority of the terms on the quadrupole are of the broadband in nature, and so when we go about trying to predict or think about what the source mechanisms are, looking at this equation from this standpoint, we generally look at the thickness and the loading noise, and we do not use this approach to calculate the quadrupole because of just computational expense. And actually what we end up doing is sort of relying on some more semi-empirical methods to determine what we think the broadband components are. And that's what I'm trying to show you here on this slide is when we talk about broadband contributions to an isolated blade, what are we talking about? And you can think of here, first of all, on the left-hand side, essentially the first mechanism we talk about is the trailing edge noise that's due to the turbulent boundary layer on the rotor or blade itself. And so as you can see, what we've kind of got progressively there, if the blade is initially at a zero or very low angle of attack, then what you have is really just that turbulent boundary layer interacting with the trailing edge of the blade. And then you also have some of those volume mechanisms we talked about in the wake. But then as the angle of attack increases, as you might imagine, the characteristics of that turbulent boundary layer change, and we get some additional mechanisms. For example, that boundary layer separation in the middle picture, or ultimately as that angle of attack increases, we'll get separation, a large scale separation, and you get a much different characteristic to that broadband nature. And so in addition to that turbulent boundary layer trailing edge noise, on the left-hand side, we also have additional broadband mechanisms due to just the laminar boundary layer. So if we have a laminar boundary layer on the blade, then you're going to get some vortex shedding, and there's actually a broadband mechanism that comes in. In addition to that, you can imagine that the characteristics of the trailing edge matter, and so if you have a very blunt trailing edge, you can obviously get a great deal of vortex shedding, and that can lead to some blunt trailing edge noise. And then finally, if this blade is generating lift, you're going to have a tip vortex, and there's going to be some broadband noise due to that tip vortex. So in sort of a general big picture point of view, there are those tonal or those what we'll call deterministic sources, and then we also have a series of broadband sources that can have an influence as well. And so just to kind of show you how some of those come about when we then look at what the actual acoustic signature of something, of a propeller or rotor looks, we've got an example here of just, these are not measurements, these are some predictions, but what I've shown you on the left-hand side there is just a completely isolated propeller that's rotating in free space. And what I've also drawn on there is you can see a vector V sub F that shows you the forward flight velocity. And what we've got are, first of all, an arc of observers that essentially span from directly in front of the vehicle to directly behind. Those are polar angles essentially from 0 to 180 degrees. And then we also have a ring of observers that are in the plane of rotation of the propeller itself. And those span that whole 360 degree azimuthal angle set. And just keep those in mind, because what I want to do is just kind of show you what the characteristics then of some of these noise sources look like. And as an initial example there on the right-hand side, what I've just shown you are three predictions for that isolated propeller itself at 0 degrees angle of attack and at a nominal kind of takeoff RPM. And what you notice there is for that case, there's at 0 angle attack, there's nothing but steady inflow into this propeller. And so you have what we call, basically steady loading on this propeller. And what you see then is if you look on that right-hand side for those observers going from 0 to 180, that you have a great deal of noise or there's a large contribution in plane at 90 degrees, and those tend to fall off in the front and in the back when you have this steady loading. And what you're actually seeing here as well is that in plane, because the loading is steady, those in-plane observers are seeing a large contribution due to the thickness, and you're seeing not a large contribution due to loading because of the steadiness. So to kind of take you then a step further from that is, we talked there about steady loading. Well, what happens if we get into a situation where we have some unsteady loading? And so what you find is that in flight, because we're generally going at a fairly low angle of attack in a steady horizontal flight, you find that those steady loads are typically major contributors. However, when you have, for example, low tip speeds or perhaps at takeoff or at landing, what you end up with is the fact that you end up with some non-uniform inflow coming about, and then unsteady loading noise can become an additional important feature. And sort of give you an example of that on the lower left, I've kind of reproduced that earlier figure with that isolated propeller, but you notice now I've labeled alpha, the angle of attack there. And instead of it being at 0 degrees, we've put that propeller at an angle of attack of 9 degrees. And what I've plotted for you on the right-hand side are those same 3 prediction methods that we've got. But what I'm showing you now is the difference in noise from when that propeller was at an angle of attack of 0 degrees. And you can see that all 3 of those, while the 2 labeled CFD predictions are a little bit more consistent than the third one, all 3 of them, as you can see, predict a non-negligible effect of the unsteady loading at that angle of attack. Again, that plot there is the difference between what the loading was at 0 degrees and what it is at 9. And so you can see for observers from 0 to 180 are in the upper quadrant of the azimuthal angles, see a decrease, and then the observers on the lower half actually see an increase. And so you can see that unsteadiness can be an important factor. And then in addition to the unsteady loadiness, they're due to, like, for example, of an angle of attack. As we mentioned earlier, this turbulence ingestion can give you quite a difference between what that propeller would look like in just static conditions versus flight. And so essentially what happens in this case, as we pointed out there, is that for the static case, these unsteady loading can increase the contribution at higher harmonics. And to kind of give you an evidence or show you an example of that, in the lower right-hand corner, we've got these are just measurements of an isolated rotor in an anechoic chamber, and the red spectrum is the measured spectrum when this rotor was in a clean environment. And then as it's run further in the anechoic chamber, what you end up with recirculation in the chamber, and you end up with a spectrum that is, they're labeled in blue, that we labeled, quote, the dirty inflow, or basically the inflow that now involves some of that additional turbulence due to the recirculation. And you can see a large increase in the higher harmonics there. So that's just sort of 2 examples of what we call unsteady loading and how that affects the overall noise signature. We had mentioned on that earlier slide, those were just talking about the isolated rotors. Obviously, something has to be turning that rotor. And so in this case, we sort of focused on electric motor noise, but you can imagine that if you have an internal combustion engine turning it, you're going to have noise sources from that as well. But as an example from electric motors, these can be comparable to the amplitude of the propeller or rotor noise. And part of the reason we have to be even more cognizant of that is that it's usually in the frequency range of human sensitivity or high sensitivity. And in the lower right-hand corner there, we sort of show you an example of some measurements where you can see the propeller blade passage frequency that's labeled, but in that red box, you can see these additional tones that are due to the actual motor, that electric motor. And in that case, some of those sources are the cogging torque. You can have resonance due to the internal cavities within the motor itself. There are electromagnetic forces, and then you can even have structural vibration of the housing. And in addition, there are, to the mechanical, there's depending on the waveform that's going into the motor itself, you can have additional sources due to those effects. And as I mentioned, this was an example for an electric motor, but if you had an internal combustion engine, sure, you've got additional kind of contributions, and you might need to use something like, obviously, a muffler or something like that. So that was kind of my attempt to show you all some examples of what the isolated sources look like. And I'm going to turn it over to Nick here and give you an example of what some of the installed sources look like. So, Nick, go ahead, sir.
All right, thanks, Doug. So yeah, we'll start talking about some of observations that we've made related to installed rotating blade sources. So the first one I'm going to talk about is rotor airframe interaction noise. And as Doug was pointing out, you have steady loading, you have thickness noise associated with an isolated rotor. You go ahead and introduce an airframe in relatively close proximity, and that's going to complicate things. So basically, you get increased acoustic levels that tend to be primarily tonal in nature. They're going to be harmonics of your fundamental or your blade passage frequency. And in addition to that, in addition to the rotor being a primary radiator of noise, the airframe itself can also double as a re-radiation source. So especially in VTOL conditions. So to kind of illustrate this, in the upper right is an image of a setup that I built in one of our anechoic chambers, and you can see the rotor on kind of like a tower arrangement there, and there is an airframe, which is essentially a cylindrical rod that is brought in from the side, and we varied the relative vertical spacing between the airframe top surface and the rotor tip. So basically, we varied the rotor tip clearance. So the location of this airframe can be very important in terms of your resulting acoustics. So in the lower right, I've provided some spectra where we basically vary the location of the airframe relative to the rotor in terms of that delta quantity normalized by the rotor radius. So in blue, that is when it's basically the closest that I could get it, which is 10% of the radius below the plane, and then 30% and 50%, and then those are all compared to the isolated rotor case, and also the motor-only noise, just for some reference. So what we see is that when the airframe is relatively close to the rotor plane, it's very harmonically rich. The fundamental blade passage frequency is that first tone that you see about 180 hertz, and then you've got harmonics of that, and they don't fall off until reasonably after 1 kilohertz. So a lot of tones, the resulting integrated levels can be very pronounced relative to the isolated rotor. But then what we see is that as we go ahead and move it away, even a slight increase in that rotor tip clearance, increasing that separation distance, can dramatically reduce the harmonic noise. For example, if you go to 50% of the rotor radius below, the resulting acoustic content is very similar to the case of an isolated rotor. Now, this isn't necessarily going to apply to everything, but it's just kind of an illustrative example. Other things to consider are prop, and inflow distortion noise, and this ties into what Doug was talking about related to unsteady loading. So if you have props within close proximity, you can corrupt the clean inflow conditions. That can harm also the propeller performance, increase unsteady loading noise, and you can also get tip vortex interactions under right or wrong circumstances. Also, airframe surfaces located upstream or above props or rotors, kind of respectively. An example is a pusher prop configuration. You can ingest a lot of turbulence into your rotor or propeller disc area, get inflow distortion, and increased blade unsteady loading noise. So, and in terms of ways to kind of mitigate some of these noise sources, we've drawn up just some general thoughts and a couple of current and possible methods of reducing these noise sources. So there's no one silver bullet for, quieting these mechanisms. They're very configuration dependent. So the acoustic sources typically scale to a fifth power of velocity or higher. So general practices, general thoughts are reduce your rotor tip speed or your jet velocity, and definitely don't discount the importance possible importance of unsteady loading noise, such as angle of attack effects, turbulence ingestion, some of those things that we just went over. Some things to avoid include gaps and blunt trailing edges, so you can reduce your blunt vortex shedding noise off of your blade trailing edge. Definitely consider broadband noise contributions, but for every rule of thumb, there are definitely exceptions. So I'll go over these real quickly. Some current methods of noise mitigation, some ideas when you're looking at fundamental rotor and prop noise, adjusting your blade count. Sometimes a higher blade count will benefit you acoustically. It's not one silver bullet, but it's one thing to consider. There are different optimal blade shapes, whether you're looking at hover or forward flight conditions. As Doug was talking about electric motor noise earlier, there are some things like if you get a higher pole count, higher magnet count, you can reduce your cogging torque noise, which is an important contributor. And speed controllers with cleaner, higher quality waveforms can also help. In terms of airframe interaction noise, like we said, increasing the distance between your rotor and airframe can help a lot. And also keeping your rotors above the airframe versus below will help you out a lot as well. And then in terms of multi-prop, and inflow distortion noise, there are games you might be able to play related to relative phasing and rotation directions to one another, not having them too close to one another, and definitely be concerned about pusher prop configurations or when the airframe is above the rotor. Some newer methods for noise mitigation include distributed electric propulsion, which can be applied to either rotor or prop reference frames. Distributed fans are also a possibility. Rotor prop noise can be mitigated with higher complexity techniques like smart materials, SMAs, such as blade morphing capability. There's also stacked and unsymmetrical rotors that can benefit your harmonic content, and also higher frequency devices such as really large number of blades that make up your rotor or propeller. On the electric motor noise front, there's ironless core technology, which essentially eliminates cogging torque as a component of noise generation, and also speed controllers that have sine waveforms. And in terms of rotor airframe interaction noise, there's possibilities of external liners and or porous airframe components and other active noise control technologies. And with that, I'm going to pass it back over to Steve.
Okay, thanks, Nick. So what's it all mean in terms of the goal? Well, what we just heard about is essentially the source noise and installed, but we need to get that noise from the vehicle to the measurement location. The goal, as you're, I'm sure, aware, has 6 microphones placed on a 50-foot radius from the center. The illustration here is of the 30-foot diameter, 12-foot high takeoff and landing area, which includes that, then shows the microphone array. And so your vehicle, of course, is somewhere located within that green cylinder in the middle, and therefore the sound has got to propagate from the vehicle to the microphone. And that's going to change, among other things, the level. So some of the ways that changes, and this is very elementary in terms of propagation, is the spreading loss. So if we assume that it is a spherical spreading loss, which is a reasonable assumption, you'll see by the equation that the sound pressure level at 0.2 relative to 0.1 is changed by 6 dB reduction per doubling of the range. And I'll talk about what that means in terms of the goal and what you need to be cognizant of in terms of hearing protection in your development in a few slides from now. So going backwards, that means that the vehicle is going to be generating much more noise when next to it than what you're picking up with the microphone. Atmospheric absorption is another propagation effect, and it's frequency dependent. I've shown on the right-hand side a absorption curve for 50 meters and 200 meters. I was a little lazy and didn't regenerate one at 50 feet. But even at 50 meters, you can see that the attenuation over the frequency range up to 10 kilohertz is not that great, which means that relying on atmospheric absorption to attenuate your signal from the source to the microphone is probably not going to be a good strategy for the GoFly Noise Prize. Caveat to that would be that there is a benefit of going either higher in frequency, where you can increase the absorption, or lower in frequency, where that A weighting that I talked about kicks in. Third effect would be the ground plane, and so the sound pressure level, as shown, is being measured above the ground plane. But if you were to do some development and looking at how that works and had a ground microphone, then you could experience a 6 decibel pressure doubling relative to the free field. And a 4-foot microphone, kind of rule of thumb, will give somewhere between 3 to 6 dB, depending upon the frequency range and the surface and so forth. So there is that effect to consider, as opposed to being in, say, an anechoic chamber like Doug and Nick were talking about earlier. So I'll just, for the benefit of the next discussion, review what the criteria are. The sound pressure level is to be measured at 6 evenly spaced microphones 50 feet from the center on takeoff and landing. It will be measured using a class 2 sound level meter in decibels, or dBA, decibels relative to 20 micropascals, as I talked about with that A weighting. The S time weighting refers to a slow time weighting in which the measurements are integrated over a 1 second period. The maximum sound level is determined at the 6 microphones, and the average or arithmetic mean is the highest of the 3 values to give that sound level rating. And the higher of the two, whether it's of those 2 ratings, whether it's on takeoff or landing, will be constitute the score. And just note that that is not a measurement that's taken during the touch and go phase. So you'll see how the scoring goes on the right-hand side. From the threshold or max level at 87 dBA at 50 feet, going down to, which gives you a 0 score for noise, up to, or down to 70 dBA, and a score of about 4.25. So what's the implications of that? Well, first off, unlike some other sound metrics like the sound exposure level, there is no duration penalty in that A-weighted sound pressure level. So in the absence of unsteady inflow, and again, Doug talked about that. So if you're sitting on the ground and ingesting your own flow, that's going to have an effect. But other than that, there's no benefit for getting up and out or down and in quickly. As well, this is the A-weighted sound pressure level has no additional tone penalty. Some metrics that are used in aviation, for example, the tone corrected perceived noise level, or PNLT, has a tone penalty. There is no tone penalty in the A-weighted sound pressure level. So there's no benefit, all things being equal, of trading tonal noise for broadband noise. You know, that all things being equal is a bit of a tricky one, but just beware of that. The number of microphones makes it difficult to average or leverage, rather, source directivity, meaning that if I think I'm smart and I can shoot the sound out in one direction, and the the other directions, well, you need to be pretty narrow. That's 6 microphones is 60 degrees, and you're 50 feet away. So that's why there are multiple microphones. Each 3 dB reduction is 1/2 the sound power level. So or sound power. So if you're going from 87 dBA to 70 dBA, that's a reduction of 50 times in the sound power. So it doesn't look that way on that linear scale, but it's a significant reduction. So that means a lot in terms of the development. And then lastly, as I alluded to, the hearing protection is recommended during test and development. I would imagine that there'll be testing going on with the actual device and measurements being made during that time period. Just bear in mind that 87 dBA at 50 feet is 108 at 4.5 feet, 4.5 being half of the 8.5 foot max size of the device. And so assuming that spreading, spherical spreading, that and taking into account OSHA occupational noise exposure standards, you could take that for about a half an hour per day, whereas the 70 amounts to a 91 dBA at 4.5 feet, and that's 6.5 hours or 6 hours per day. So bear in mind, these are not insignificant sound pressure levels, and you should take the appropriate measure to protect yourself and others. So lastly, getting to the end, I just wanted to make you aware of a couple of tools that are available at NASA. And of course, there are other commercial tools available out there you may be aware of. But I'll just kind of highlight a few of these. All the software that I'm referring to here are available upon request and filling out some paperwork at the website there, software.nasa.gov. There is the ANOP code, or Aircraft Noise Prediction Program. Doug showed on one of the earlier slides this PAS, the Propeller Analysis System, that is part of the ANOP package. ANOP itself is part of the ANOP 2 framework, and if you're in the US, you can get both of those. If you're in overseas, then you're able to get only the ANOP 2 framework, which has got significant capabilities still, including the Fox-Williams-Hawking calculation that Doug mentioned earlier. If you want to hear what the sound sounds like, there's the NASA Oralization Framework, or NAF. Another tool is the Advanced Subsonic Supersonic Propeller Induced Noise, or ASPEN. For propagation, there's Acoustic Propagation and Emulation Toolset, or APET. That's a US only as well. And then finally, the Rotorcraft Noise Model, RNM version 7. And so with that, I would like to thank you, and the three of us will take any questions that you have.
Great, thanks, much appreciated. Let's jump into quick questions here. So in your development and research, have you guys ever worked with any sound dampening via motor mounting, things like rubber mounted or spring loaded motors?
Absolutely, yeah. No, I mean, we've done some wind tunnel tests where we've gotten some pretty good use out of grommets. So they've been typically smaller scale, like, you know, quadcopter grade and everything like that, but definitely illustrates the potential benefits. It's a wind tunnel rig, so it's going to be different than in an aircraft, but yeah, that can be beneficial.
And the issue there would be then the radiation or the vibration into the structure and the radiation from the structure out.
Great. And what about ducted fans? How do those affect noise?
Yeah, we actually, and another aspect of the stuff that we work on is exactly, obviously in that case, ducting can help both from an aero and from an acoustic standpoint. You know, from a shielding, and also from the standpoint of if depending on the size of the duct and the thickness of the quote the nacelle, you can actually use acoustic dampening. You can use acoustic liners in there. There's sort of a trade-off though. You're going to be carrying around extra weight, and you obviously have some extra additional drag depending on the way you've installed this and the way the whole configuration works out. So it is kind of one of those things that there's pros and cons to it, and you also have to kind of keep in mind from an acoustic standpoint I'll say the axial length, the axial extent of that shroud matters as well. I mean, if it's too short, it's just going to go around. So, but yes, there can be a benefit. Sorry, it's kind of a on one hand, I'm saying, oh yeah, there's a benefit, and the other hand, there's some, but there are pros and cons to it, and depending on the application, it can be a help.
I guess another con would be that it can generate a distorted inflow condition, which would lead to unsteady loading as well.
Unless you made it long, right?
Right,
if it were longer, then essentially it's going to straighten out the flow and kind of clean it up. So it's one of those.
Yeah, shrouded fan, also an edgewise float, so like a rotor, that's going to have a lot of additional drag issues, going like this, and just the flow going over that lip into the rotor. Yeah.
I guess the other thing I would point out to that is depending on how you mount I'll call it the shroud, depending on how you mount it. So you're going to get interactions between the struts, the mounting struts for that shroud, and the actual fan or propeller itself. So you'd have to pay attention to spacing and number of struts and things like that as well.
Great. And then are there any low noise shaped propellers that are in production for sale? Is there anything you recommend to people who might be looking for commercially available things to help with their builds?
I mean, I'm kind of looking at Nick here because I know he's been doing some tests in the low speed aeroacoustic wind tunnel. So in terms of the scale we're talking, maybe you might have, I don't know if you've seen some companies there. Most certainly companies are out there looking to do that for not only for community noise, but for also cabin noise. So that's certainly something they designed to. I don't know if you've run across anything from a.
Yeah. So I don't want to say specific brand names, but in general, what the main thing is tip speed from a fundamental, steady rotor operation standpoint. So you kind of want your prop rotor, whichever it is, to be giving you the thrust that you want, efficiently, so you're not drawing too much from your battery or your propulsive source. And you want to keep that tip speed down. So typically you want to be able to spin it at a lower RPM. So you want it to be an efficient lift or thrust generator. So sometimes blades that have a larger chord distribution, maybe one that looks more elliptical from the top or something like that, might be a better way to go. A lot of these streamline, ones that taper down to a point at the end, they have their benefits, but not typically in terms of acoustics. Kind of a general observation. Yeah, the University of Illinois, Urbana-Champaign, they have a really good prop performance database, so that's one reference.
But that will be just performance.
That's just performance. Acoustics. That is not acoustics. Yeah.
Great, thanks. And then the next question is about counter-rotating coaxial props. Any information that you can share about those, things like minimum separation or effects on thrust there?
So in general, I don't have a lot of experience with coaxial. I did work with Doug on counter-rotating prop fans or contra-rotating open rotors. But for coaxial rotors in general, you will get a little bit of a performance boost in liftoff or hover conditions. You can get an inflow benefit from the top rotor seen due to the rotation of the lower one. Acoustically, though, I don't have I don't have much experience.
Yeah, I mean, it's a good question from the standpoint of if they're contra-rotating, it's a good question in terms of the spacing, because you want the benefit of the contra-rotation basically straightening out the wake flow and improving thrust. But the closer they get, then you're going to have more of that blade wake, blade vortex type interaction that we talked about. So you have to be careful of, you might possibly change the diameter between the two so that the aft blades, or the lower ones, if it's in a vertical situation, may not be seeing as much of the tip vortex off of the front rotor. As Nick mentioned, there was a lot of work done on open rotors, in the 80s. Now the difficulty there is those are much higher speed than we're talking about here. But there's probably some lessons that you can look through and learn from those in terms of what they did spacing wise. But you'll notice a lot of the things they did was certainly what was the separation, what's the relative diameter between the two rotors themselves. So it's kind of, again, another one of those things where you certainly can come up with an aero benefit, but you got to be careful in terms of the acoustics. You're going to take an acoustics hit from it.
Thanks. And then next question is about muffling. Do you have any recommendations on muffling materials, things like fiberglass or rubber or other materials that might make good mufflers?
Wow, in terms of materials, yeah, like you said, bulk materials, fiberglass are the biggest ones that we're familiar with in practice. Other than that, I'm not sure I can offer much more advice on that one.
If you're going with an IC engine, it's probably going to be worth your while
to go look at. Yeah, I mean, and look at off the shelf kind of mufflers. Yeah, sorry, I don't have a whole lot on that one.
Yeah.
But in terms of specific materials, bulk materials will be much better at a broadband attenuation. But yes, I guess that's one of those where I'd go look at the commercial market and see what's out there.
And then you talked a lot about props and rotors, but what about things like jet engines or turbofans or turbojets?
Yeah, well, I mean, in the one slide that Nick had, you notice that noise goes as V to the N, and for jet noise, one of the things you may notice, I'll kind of a corollary here, is that from a commercial aircraft standpoint, you may notice that the diameters of the engines have gotten larger, and the reason for that was to reduce the exhaust speed. So if you were to go to a turbofan or a turbojet, you're going to incur the jet noise and effect there. And so if you want it to be quiet, you're probably going to have to go larger, which would, but the reason I say larger is because you'd want to reduce that jet speed as much as you can. And so there's nothing, I think, keeping, certainly something you could try.
It might be a pretty good weight penalty compared to propeller configuration.
I mean, if you smaller turbojet's typically going to have a higher RPM, so it'll be a higher frequency, and from that standpoint, from the fan, I'm saying, but the exhaust speeds are what you probably have to pay most attention to from the jet side.
Great, thanks. Could you just talk a little bit about the kinds of inputs that are required to use some of the noise predicting software that you mentioned?
Yep. Sure. Yeah. The Foxwings Hawkins code, for example, those kind of approaches, what you would need is you need blade geometry. So you input a blade shape, and then you would input the blade surface pressures. And those blade surface pressures can come from a CFD code. They can come from blade element codes. There's different ranges of fidelity in trying to get those. For example, the PAS code that Steve mentioned uses blade element theory to come up with those blade loadings. But given the blade geometry and the blade loading, that is what gets input to the noise prediction codes, and you go from there. So you need essentially the conditions, RPM, things like that. But geometry and blade loading is the main factor.
And we've taken some data in the past from X-Rotor, right, over into
You
PAS.
can even,
Yes.
yep.
So
Whatever
if
you
you're
want to
using a tool like that, then you can do the calculation there as well.
Yeah. Now, as far as the broadband, those are a little bit more semi-empirical. So for broadband kind of a prediction, you'd need more information about the boundary layer, which you can get from some of the blade element codes. But
Be careful with
Yep.
those. You know, panel codes and blade element codes. They might not be the best at those, based on comparison with experimental measurements. You know, could be misleading potentially. But they can be calibrated. They can be tuned potentially.
Great, thanks. And then since we're getting close to the end of time here, could you, each of the three of you, just leave us with a couple of words of advice for the GoFly competitors?
Steve, you want to start?
Sure, I'll start. While these guys can think about that. Words of advice. Okay, so primarily watch out for your due to hearing protection because it is a factor. And then I would also say there's nothing like a measurement. So even if you are particularly savvy with your analysis tools, then you definitely want to go out. Of course, it's part of the rules to fly, demonstrate that the vehicle is capable of flying, but in that process, make your measurements and look at source directivity, look at how the sound is falling off, whether it's a spherical spreading loss, as I indicated, or if it's working in a different fashion. And yeah, that's kind of it. Doug? Yeah,
I mean, I guess I'd say along those lines as well. See, not only measurements, but we've mentioned some of the tools. We don't want to spend tons and tons of time from an analysis standpoint, but even some of the simple tools can be really helpful in terms of just telling you trends and things. If you can, it probably wouldn't be. It would be helpful, I think, to take advantage of some of those tools where you can. And in general, I think those kind of 4 or 5 or 6 general guidelines that Nick had on the one slide. Tip speed matters. You pay attention to blade count, things like that. And installation. But I imagine that's probably where Nick's going to go. So
that's all you left.
Yeah, that's all I left.
Yeah. So few things. Also on the safety side, in addition to hearing protection, if you're going, exposed rotor route, be safe with the blades. There have been news articles and things like that of people getting hurt or worse with, composite blades and things like that. They can hurt you really bad. So be wary of that. As Doug and Steve also said, kind of a balance between, using maybe some sort of a prediction code to give you an idea of trends, and then you can do some sort of experiments to sort of verify that's what that those predictions are, following the right behavior. And in terms of installation sources, there's some low-hanging fruit things regard to rotor airframe interaction noise that can be pretty useful, so that it can maybe reduce the overall noise signature complexity that you're looking at. That's pretty much it.
Great. Well, thank you very much, Nick, Doug, and Steve. I'm sure the GoFly community greatly value the lecture you provided today. So thank you very much for the lecture, and thank you to everybody who was able to participate and will be watching later. And have a great day. Thanks.
Thank you.
Thank
Thanks
you
for having us.